Same disclaimer as always, take the test, then look at the answers. If you get something wrong, please mark it wrong, be honest with yourself, and email me your score out of 35 points no later than Monday night at midnight. 15 is a lot like question 14, except we're not being asked about the acceleration, we're being asked about the displacement. And remember, the word displacement is a synonym for the change in position. So what we really want to do is figure out the position at time 0 and then the position at time 6 and see how much it changed. But we don't have a position function, we have a velocity function. So what do we do with a velocity function to go to a position function? We have to integrate this function. When you integrate a velocity function with respect to time, as shown here in the second bullet point, you get the displacement or the change in position. Right now I've left that as an indefinite integral, but we're going to put the limits on here now because we know that we're evaluating it from time 0 to 6. So that's what these notations mean, starting from time 0 and ending at time 6. And the integral of 4 plus 1/2 t squared dt is going to be a power rule problem. So 4, remember, is sort of the same as 4t to the 0th power, because anything with the 0 is just 1. So it doesn't show up here, but you can think of that as 4t to the 0. So when we integrate anything using power rule, you just add 1 to the exponent. So t to the 0 becomes t to the 1st, and then you divide by the new exponent. So 4t to the 1st over 1, which is just 4t. 1/2 t squared, same rules apply. So you always raise the exponent, so 2 will become a 3, and then you divide the entire expression by the new exponent, so it's 1/2 t cubed over 3. You'll notice here that I've simplified the fraction, so 1/2 over 3 is the same as 1/6, and everything else is as I said. I've also integrated here, so I no longer need my integral symbol or my dt, but I will keep my limits of integration here. I want to evaluate this function at 2 different moments in time and then find the difference between them. So this will tell me at 2 different moments where am I? Where am I at 0 and where am I at 6? So to find the answer for how much my position changes or displacement, I'm going to plug in 6 to that function and see what comes out, and then subtract plugging in 0. So when you plug in 0, since t is in every term, this just goes to 0. This whole minus everything here in brackets is nothing. So all we really care about is what is my position at time 6 seconds. So you end up with 4 times 6, which is 24. And then 1/6 times 6 cubed, you can actually just cancel a 6, right? This is the same as 6 squared then. So it's 24 plus 36, and the answer is therefore 60 meters. And we want to figure out at the lowest point how fast is it moving. The first thing to think about is how could you figure out speed? Well, what models might be valid here? It's moving in a circle, in circular motion, so we could maybe try circular motion. Momentum is not going to be conserved because gravity is a external net force on the pendulum, so we can't use momentum. Energy would be valid because even though there is a non-conservative force from the tension in the string, the angle between the tension in the string force and the instantaneous displacement is always 90, right? Because the tension is a radial or centripetal force, and the instantaneous velocity is always tangential, and so there is no work done by any tangential force. Therefore, you can use energy conservation here even though you have a non-conservative force. Gravitational force is present, but it's conservative, so that's fine. You can still use energy conservation. Kinematics. Cannot use kinematics. The acceleration of this object changes. It's going to change. So what would be the best way to go here? Probably either circles or energy. Let's first just figure a few things out. We know the ball starts at some height. We don't know what height that is. And then it descends to some minimum vertical position. Let's just try to identify a few things here. When it goes to its lowest point, it will still be a distance of L from the pivot up here at the top, right? That's just the length of the string. We also can form a right triangle here, and this will allow us to sort of determine a few of the distances. So if you break this apart using SOHCAHTOA, this side of the triangle would be given by L cosine of theta, where theta is 60. Okay, and that means that the distance delta y that this ball travels from its maximum vertical position to its minimum vertical position is delta y, or it's L, the whole length of the string, minus L cosine of theta, which is this side of the triangle. Delta y is L minus L cosine of theta. You can factor out an L here. You don't have to, though. You could also just go ahead and plug in a 60 for theta here, because cosine of 60 is 1/2. So this would just become 1/2 L. I'm not going to do that, but it's valid. You get the same answer. Anyway, I'm going to now try an energy conservation approach, and you have an M on both sides. Well, you know what? Let me back up and just explain what this says first. So I have mgy. Mgy is the initial gravitational energy at the height shown here. Okay, and this assumes then that I'm setting my y equals 0 point to be this dotted line, which is the lowest point in this swing. I set my y equals 0 here because it's a choice you get to make, and if you set it here, then at the bottom of the swing, the ball has no potential energy. All of its energy is then kinetic, and that makes my analysis simpler. But now I can say again, like I started before, the m's cancel out, we lose the m's, and I can change y, the initial vertical height here, is L times 1 minus cosine of 60, and that's just this expression from above. Okay. And then 1/2 v squared is the same thing on the right. I'm going to just now solve this for v. And we end up with the square root of GL. And we're trying to figure out the change in kinetic energy. So if you were to express that symbolically, the change in kinetic energy is delta K. And it turns out this is something we have a formula for. You guys remember doing the network kinetic energy theorem? That's the one that says that the change in the kinetic energy of an object or a system is equal to the sum of all the work done on that system. So, since we're being asked for delta K, the answer is just the net work. Now, that's not explicitly listed, but the net work would just be the work done. Let's write this out so you know what I'm talking about. The net work, you could just use the formula for work, right? It would be FD cosine theta, so that would be net force D cosine theta. I'm not going to write the cosine theta here, but it's really present in the formula. So anyway, the answer is the work done by the net force, which is A. I'm willing to bet that some of you saw the words simple harmonic motion and immediately thought you don't know how to do this. And it's true that we haven't had a unit on that yet. That's our last unit. But you can still do this question because it's really just a graph question and an energy question. So look at what we start with. This is a position versus time graph, something you're very familiar with. And on a position versus time graph, you know that the slope at any moment gives you the velocity. So for instance, like right here at the top and right here at the bottom, the slope is instantaneously 0, and therefore the velocity is 0 at those two moments. Whereas the velocity or slope is positive at the beginning, and it's sort of negative in the middle, and then it's positive again at the end. So you know how to convert this to a velocity versus time graph if you were asked to do so. You're not doing that directly, but you need to know the velocity at different moments in time because you're asked for which of these is the graph of the kinetic energy, the K value. Well, what's the formula for kinetic energy? It is 1/2 mv squared, or I'm going to just say proportional to, that's a pretty crappy proportionality symbol. Let me try that again. Proportional to velocity squared. So it will qualitatively look just like the corresponding velocity squared graph. So let's just kind of think of what that would look like. So we know that this is essentially just a sine wave, right? You guys have probably figured that out. This looks like the sine function, assuming that t here is 2 pi, which is the period of a sine wave. That means that the derivative of this, which would give us the velocity time graph, would just be the cosine wave, which I'm going to try to sketch. Nope, no I'm not, because it's already an answer choice. The cosine wave is here in answer choice A, and if you got this question wrong but kind of knew what you were doing, you probably chose A. And the reason is, yeah, that is the correct velocity versus time graph, but you're not being asked for velocity. You're asked for a graph that matches velocity squared, and therefore it can never be a negative value. So all of this stuff in quadrant 4, where it shows a negative kinetic energy, you just flip it upside down, and then the answer that is correct is B. Let me scratch out A so there's no confusion. B is the right answer here. Of the time, but as a function of the displacement. This one is a tricky question. A lot of people have trouble with this question. The best way to do these, basically invent a graph or find the matching graph kind of questions, is to just look at some of the local extrema, like on the original graph. So, like for instance, let's look here at the apex and just think, what do we know at some of these moments in time? And if you can just get some of the graph points, you can probably guess and at least narrow down your choices. So we know here at the top, the slope of this position time graph is 0, and that means at this instant, the velocity is also 0. Same goes here at the valley. Velocity is 0. Okay, so at the moments that velocity is 0, what is true about the position? Well, position is being graphed on the y-axis, see here. No, that's somewhat counterintuitive, right? Like the x is on the y-axis, but it just means position. It doesn't mean like the x-axis. So if position is being graphed here on the vertical axis, then what is true about position at this moment at the top and then at this moment at the bottom? Well, that is the largest or the most positive position. This is here at the top. And at the bottom, that is the most negative position anywhere in the path. So what that tells us is we need a graph where at the most positive and at the least positive, or I should say most negative positions, we have a velocity of 0. So let's try to figure that out. So all of these go into the negative region, which makes sense. We're looking for a graph where at the most negative and most positive position, velocity is 0, and therefore kinetic energy would also be 0. So this graph at the most positive and most negative has a positive kinetic energy, so that can't be right. This graph, B, I'm looking at now, at the most negative position has a negative kinetic energy, and at the most positive position has a positive, so that can't be right. C has a 0 kinetic energy at the most negative and most positive positions, so that's a possibility. Same goes for D. That's a possibility. And E is wrong for the same reason that A was wrong, because it has a positive kinetic energy where it needs a 0 kinetic energy at these moments. Okay, so now which one is it? C or D? Well, we're going to need at least one more point to figure it out. So I would just kind of look at C and D and say, what's the major difference between them? The middle, basically, right? So at the middle, C has the maximum kinetic energy during its path, and D has a 0 kinetic energy during its path. So we need to look in the middle and determine when the kinetic energy is, or no, let me rephrase that, when the position is 0, which is the y-axis on these answer choice graphs, when the position is 0, like that, and I'm really bad at drawing with this thing. This looks kind of like a bird. Anyway, we need to figure out the kinetic energy at that moment. So let's go back to the first graph. When the position is 0, that would be the x-axis on this graph, right? Any deviation from that line represents a non-zero position. So what is true when the position is 0? Is the kinetic energy maximized or minimized? Well, at every moment this line crosses the 0, it has a non-zero velocity, and therefore it's impossible for it to have a 0 kinetic energy. So the answer is C. In order to answer this question, you have to know something that you won't know unless you watch the lectures and the playlist Unit 9, Momentum and Impulse. So if you haven't done that yet, go do that now. And if I'm not mistaken, I think the lecture that pertains to this question is number 7, Applications of Angular Momentum Conservation. So I'm going to continue now, assuming that you all seen the video. So the first thing you need to just know, it's just a fact, is that anything orbiting has a constant angular momentum. So we can eliminate answer choices B and C. But because it doesn't always have the same radius, so let's look at y and then let's look at x here. Clearly, those are different distances. X is farther from the sun. Because it has a different r value, but L is conserved, and L is equal to I omega, that must mean that when you're closer to the sun, your rotational inertia is smaller, kind of like the dancer pulling her arms in during a figure skating maneuver. And therefore, to keep the angular momentum constant, your omega must be increasing. so that there's a constant L value. So this is exactly the same kind of question as the figure skater. So if I goes down and omega goes up proportionately, what does that do to the kinetic energy? It increases it because, oops, I forgot the I in the energy formula is to the first power and omega is to the second power, and therefore omega has a larger impact on kinetic energy than does rotational inertia. So the answer is D. All right, we want a constant gravitational field strength. So that's just the force of gravity, the acceleration of gravity. We're going to first find a formula that allows us to express the force of gravity in terms of these things like radius and mass. It's Newton's law of universal gravitation, which tells us that the gravitational force anywhere in the universe is equal to g, which is the universal gravitational constant, times mm, the two masses that you're trying to find the gravitational field between, divided by the square of the distance between the centers of those masses. That's what r is, distance from the center of m to the center of little m. So the question is basically this. If I quadruple the mass, right, that's in the numerator, and I need the gravity to be the same as it is over here, well then what must happen in the denominator? Well, it must also have a 4, right? We're going to need a 4 down here so that 4 over 4 cancels, and we end up with the same expression, the same gravitational force. But you can't just multiply the denominator by 4. You can't put in a 4 like 4r because it's being squared. So you need a number which, when squared, becomes 4, and therefore the answer is 2. If you double the radius, then you have the same gravitational field strength on Cosmo that you would on Earth.